Thank you very much, Rama. So I'd like to thank Professors Rama Govindarajan, Sandeep Trivedi, Rajesh Gopakumar for inviting me to talk in this very, very interesting workshop. We've had wonderful talks on the first day, and I couldn't have asked for anything better than the talks we had today to set the stage. Regarding aerosol, representation in GCMs by Professor Liu, and now, of course, the very, very authoritative talk by Professor Krishnan regarding development of Earth system models. And then, of course, he's talked about the very exciting history as well. So as Rama said, I'm an aerosol scientist, and here I think what I'm going to try to do is to look at how aerosol influences then couple with or have feedbacks to climate variables via dynamics, via atmospheric energetics, etc. And see what is it that with the approach that is typically used, a lot like what Professor Liu said in the morning. So with that, it's always nice to start with a really complicated slide that says, here's a whole host of things happening, and all of which Dr. Krishnan has looked at and alluded to in terms of their inclusion in Earth system models. So this comes from a huge paper we wrote a while ago as a review, which is talking about black carbon or sooty aerosols and bounding their climate effects, and did a sort of huge scientific assessment of it. So then, we have aerosol emissions, and we'll talk about where these fundamental processes come in, which could be looked at a little better. And then we have aerosol mediation of atmospheric radiation of clouds, both in terms of their what is called macrophysics, the cloud heights, the cloud widths, the cloud anvils, as well as microphysics, which is to do with altering cloud drop sizes and cloud drop spectra, and how that then, affects radiation, of course, but it also affects precipitation. And then, of course, there's, various other effects of aerosols, and Dr. Krishnan alluded to the fact that the mean global temperature is cooling because a lot of the aerosols are scattering. But then I will try to give you some idea about, where you have absorbing aerosols as a predominance, which is in the Indian region with dust and sooty aerosols. What are the differences that we find, and where are, the processes that influence them? And then aerosols are important to the cryosphere as well, because for one thing, of course, any near surface temperature changes then feed back to snow, melt, snow cover, etc. But also that by falling on to snow surfaces, which is called dry deposition, aerosols are then changing the reflectivity of the snow, which is called snow albedo, and therefore then leading to greater absorptions and so on. So the approach we take in my group, because we are model users and not model developers in the way that Dr. Krishnan talked about, is we first, of course, look in observational studies to extract various effects of aerosols on temperature, clouds, rainfall, etc. And I'll talk about some of these. And having extracted some of these effects, then the question is, what are the underlying mechanisms? how might some of these effects change if we could, do better on some of these mechanisms, etc. And of course, Dr. Krishnan had talked about what he called the coupled models, where you have the ocean atmosphere coupling, and therefore sea surface temperature becomes something that is estimated or predicted, or is a prognostic variable, as we call it, in these coupled models. And so then what all changes act via the modification of sea surface temperature. Those are what are called slow responses, while you have not just sea surface temperature or SST kinds of effects, which of course take longer periods of time, given the huge heat capacity of the ocean. But you can have fast responses of the atmosphere to various perturbations. And these fast responses essentially take place by altering atmospheric temperature lapse rates, as they are called, the vertical profiles, by altering pressure gradients, temperature gradients of the surface, north, south, east, west, etc. And, all the cloud microphysical and other effects are essentially fast responses. So with this kind of an idea that, we now have to find a way to maybe disentangle the integrated responses and the fast responses, I'll just go forward. Let's start with temperature extremes. All our, let us say, basic understanding of climate change comes from the fact that we are warming global atmosphere, and the fact that, we are talking about the fact that we want to then have agreements in terms of limiting this warming. And then also with the background then that when we inject aerosols, certain types of aerosols, which are the sulfates, nitrates, and organic carbon, are treated in terms of scattering properties only, while of course aerosol scientists have some new ideas that all of organic carbon may not be a pure scatterer, etc., etc. But then we have two very, very strong absorbers. One of them is black carbon, and this is a study that I'll point to. And another one, of course, is dust. And in India and over the Indian region, the aerosol is dominated by what we call mixtures, and we don't have to get into that. No aerosols, exist separately, but they're all the mixtures of the absorbing and the scattering kinds in real particles. So what is known about heat waves and about the heating that's going on in our region is, there's large scale atmospheric dynamics linked to it, which is a North Atlantic blocking, and you have a subsidence that is going on over a large part of India. Then you have the depleted soil moisture, precipitable water content, goes down, you have clear skies, etc. And this has been shown by various people. And what we've talked about in terms of surface temperature cooling. But what's really happening to the extremes, as well as, in some cases, the mean temperature? So in fact, Krishnan and Ramanathan were the ones who first showed that, you have cooling trends in the dry season when aerosols abundances are large, but that the cooling happens almost sort of where the aerosol is located, because the downwelling radiation to the ground reaching radiation is cut off. But then evidently that aerosol is in a layer and it is absorbing radiation. So then you have to have some non-local warming. And so that was the caveat there. And then the other sort of very interesting study, which is a model study by Van Weiss et al., who show that if we inject black carbon at different altitudes, then you may have a surface temperature response if you inject it very close to the ground, which is a warming. And this is from the diabatic heating of surface air. But, when you go on to higher altitudes, 12, 20, 29, etc., you have a cooling because there is a sort of a more efficient release of radiation to space from those levels. So with this background, then what are the things that we have found? So when we looked at a long data set, 1979 to 2013, the aerosols are detected by various satellite products, and it's called aerosol absorbing index. And this aerosol absorbing index is a columnar property. So, we kind of, this is telling us how much absorption is there in the entire column of the aerosol. And so if we look at, temperature maxima, because that is what drives the heat waves, then T2 meter maximum temperatures, and with various kinds of statistics, which I won't go into, you see an increase, a certain, decadal increase, particularly in Northwest India. And in the same region, you also have the absorbing aerosol increase. And I'll come to causality. And so, firstly, a cross correlation showed a very interesting thing, that local aerosols, because of diabatic heating, so this is the correlation between aerosols in the Northwest and temperature maxima in the Northwest, that exists. But here is the non-local heating effect, which was alluded to by Krishnan and Ramanathan, that there seems to be a correlation between increases in central India aerosols, which somehow with heat diffusion then also correlates with the temperature maxima in the Northwest. So with this kind of observational study, we use general circulation models. Again, I mean, the reason why we picked ACAM 6 HAM2, just like Dr. Krishnan was saying, we wanted a model that had, for us, a very detailed representation of aerosols. As Dr. Liu was pointing out, you need microphysics, you need chemistry, you need a wide variety of production and loss terms, and so on and so forth. So this model has all of them. It is a European community model, sort of originating from Max Planck Institute of Meteorology. But there's a large community, and we chose to run this model also because at the time we were also looking at monsoon. And so we wanted to find a model that had some fidelity for reproducing the monsoon, reproducing the teleconnections and drivers of the monsoon, and ACAM 6 HAM2 was, the model of choice. And so what we find in the model is that the various, I'm not showing that, the approach that's typically used is either we do a simulation where we have all the forcings, greenhouse gas, aerosols, etc., and we extract maybe a composite of whatever effect we want to show, and then say, in that composite, can we discern an aerosol effect? Okay, that's one. Another is, of course, to do simulations with differing levels of aerosol effects. And I'll also say over here that the way we run this model is not as a coupled model, but what's called an atmospheric general circulation model, where the sea surface temperatures are pretty much given to the model. And so we can give it from observational data sets and decide whether we want to, have sea surface temperature in an evolving state or in a fixed state. And so what we find from this composite kind of analysis here is we detected all the large-scale meteorological changes that were shown by Rohini, Ratnam, and so on. But in addition to that, in the hot composite, we had an enhancement of the absorbing aerosols and what is called the short wave heating rate forcing in Kelvin per day. So this forcing means it's a double call to the radiation transfer model, and basically says that we are calling the radiation with and without the aerosols. So this is the effect because of the presence of aerosols. And so we confirmed not only the large scale dynamics, but also the fact that there is an aerosol effect and a certain mechanism related to it. So, once again, Dr. Krishnan had shown Rama is trying to ask a question.
Hello, can you hear me?
I can hear you now. Not now.
Hello?
Yes.
Can you go to the previous slide?
Yes.
So, like I have a naive question. You are putting aerosol as input at initial time, and then you're allowing it to evolve, or if there's aerosol forcing at different times, you're allowing this.
Okay. So these are what are called, fully coupled models with prognostic aerosols. And so we are introducing emissions of aerosols at every time step. So that it turns out to be a boundary condition. And all the aerosol physics, chemistry, etc., is being calculated by the model. On the time step is a little longer than the meteorology time step, but this is a fully coupled aerosol model which has prognostic aerosols. What Dr. Krishnan said this morning is because they were trying to do long-term simulations with for climate, they had used the aerosol optical properties prescribed into the model, then to see how the dynamics and other things change. So here, and the aerosol emissions, I didn't say it, but my group has another activity where we develop this emission inventory for India called Smog India, speciated multi-pollutant generator. And so we try to customize the emissions for our region. So just quickly, and I'm not the expert on this, so I'm not going to dwell too much on it, that there were various processes that mediate the temperature response. And what we're saying is that, we have a surface energy balance in terms of various fluxes, latent heat flux, sensible heat flux, ground heat flux, etc. But one of the things which is sort of, I think I can just say it here, is that the lowest model layer would extend 30 meters or so. And we, have to understand what is the turbulent heat flux, turbulent heat transfer that's taking place. And these are in a given model in the land surface module. We would have, some of these as well as some of these in terms of parameterizations at the surface. So this, I think, is one thing that where people with fundamental interests can look at a little bit more carefully. So what is one other thing that, land atmosphere coupling does? We had talked about aerosol loss processes. Dr. Liu had mentioned it, that there is this thing called aerosol dry deposition, which is, really to do with, we take a concentration at the surface layer, and there's a lot of physics that goes into developing this thing called a dry deposition velocity as a function of aerosol size as well as aerosol properties, right? And then it is sort of looked at in terms of the fact that you have an aerodynamic resistance, what is bringing the aerosol close to the surface. And then we have the quasi-laminar resistance, which is how does the aerosol transfer across the viscous layer, which is very close to the surface. And so what we find over here is that particularly both of them depend on friction velocity, right? And this is, of course, our very familiar logarithmic, formula. But the fact that friction velocity and all of these have to be parameterized somehow. Within that 30 meters, what is the vertical profiles of anything is something the model can't calculate. So it has to be told. And this you can, maybe ignore because people are more interested perhaps in the fluids aspect than in the aerosols aspect. So I'll just skip over this. And so one of the things that, I kind of did not say explicitly, I'll say it here, that over snow surfaces, the deposition velocity or the deposition fluxes are highly underestimated. Are overestimated by models. And so this has something to do with the fact that you have slip over these snow surfaces. It's not, the fully rough surface assumptions may or may not hold, and so on and so forth. So models are overestimating hugely the amount of flux of these particles to snow surfaces, and it has something to do with not quite getting these friction velocities right and not quite getting these transfer rates right. Another sort of important thing, location where friction velocity becomes important, is to understand dust emission. So dust emission is calculated by the model in every time step, okay? And there is this concept of a threshold friction velocity. Only above this will you have dust getting kicked up. And I'm not showing, the vertical flux and the horizontal flux formulas over here. I just want to say that this friction, this threshold friction velocity then has some uncertainties in it, and therefore it has to be tuned. So, once again, we come back to the point that at the land atmosphere coupling, we found that dust emissions over India in this ECAM ham model that we used were rather too low. And then we were able to code into it at least some sort of, tuning. So these are sort of changing the tuning parameters, some of which Dr. Krishnan mentioned, in order to get the right amount of dust to kick up. So, all right. Let me shift gears here, quickly go to cloud microphysics and macrophysics. So once again, I mean, if you look at the fact that we have a large number of processes, this is from Ulrike Lohmann, and this is in ECAM. The ones that are within yellow are the ones that are, maybe mediated by aerosols in an explicit way. And we want to look at, some of these processes. The kinds of cloud responses to aerosol radiative effects are, for one, that absorbing aerosols, when they stabilize near surface atmosphere, it is suppressing a moisture convergence or a moisture transport to the upper levels. And so what that really leads to is a negative cloud feedback. So you have less clouds forming. That allows more radiation to reach the ground, further stabilization, and this becomes a feedback that further reduces clouds. And then there is this other thing that when you have dust as well as biomass burning sooty aerosols injected into clouds, you sort of have some kind of a burn off of droplets. because of the within cloud heating. And then, you end up prolonging the cloud lifetime. So clouds contaminated by dust, etc., it lowers what is called the liquid water and the ice water content, called LWP, IWP. There's another, of course, it's a very famous paper, 2008. Everyone must already have read it, which is to do with the fact, yeah, Rama.
Could you go back to the previous slide?
Yeah.
Yeah, can you explain what is aerosol optical depth and tell the units it's in?
Okay, so aerosol optical depth is like in extinction over, so it is, suppose you had your I by I naught is equal to minus exponential of bx, but this is integrated over the entire column, so it's unitless, so it's exponential of minus tau. So it is the amount of radiation extinction, if you would, which is happening from top of atmosphere to surface because of the aerosols in the column. And it is, of course, given as a function of wavelength, and it varies as wavelength. Okay? Yeah. And so it is detected by satellite sensors. There are multiple satellite sensors. So one of the best characterizations of aerosol spatiotemporally is aerosol optical depth. And, then we have, of course, Daniel Rosenfeld and colleagues' paper over here, which is saying where you have polluted clouds at the base of the cloud, you have a lot of pollution, you're reducing the cloud drop sizes, and therefore you have a greater lofting to higher heights. You have this freezing and then, recondensation. And this is like a heat engine within the cloud that allows the cloud to grow much taller, to have this really wide anvil, and this is called the cloud invigoration effect. And while this is, known offline, it has been modeled offline, most general circulation models do not capture this. And this is just, basically showing that aerosol optical thickness is equivalent to AOD. It keeps going up, the transmission keeps going down. But, you initially have this kind of increase in the heat pump kind of effect with an increase in the CAPE, or convective available potential energy. But after it pushes up, then you have a stabilization. So even within the cloud, the amount of heating then tells you whether you're going to have an invigoration or you're going to have a suppression. All right. Then this other thing, which people who are interested in clouds would really be interested in seeing, is that we have this idea that with clouds, the moment you inject more particles into it, you get smaller drop sizes. This thing is called the Tumi effect, TWOMEY. And it's an instantaneous effect that assumes that you have a limited amount of moisture, which distributes over much larger numbers of particles and gives you a smaller particle size, right? So this Tumi effect then increases the reflectivity of clouds. But now we have droplet effective radius and aerosol optical depth, which is now a proxy for number of particles. And there are some regions and some situations where there is an anti-Tumi effect, which is you're increasing the numbers of particles, but instead of decreasing the mean droplet size, there's an increase. And this has been detected over warm, polluted, humid regions, Gulf of Mexico, South China, et cetera, and it's not yet explained. And we detected the same thing in two of our studies where this is effective radius, increasing with increasing aerosol optical depth, and this is over India, and this is for, you know, region 1, region 2, region 3, and it was at that point a smaller data set, 2000 to 2009, that was available. And so we're seeing a sort of Antitomy effect, which is not very easily explained. And we've taken a look at that. This is, you know, work in progress, where we are trying to do a much better job of evaluating it, both over land and over ocean. So this idea that the delta change, of course, logarithmic in effective radius divided by the availability of aerosols, if you would, as AOD, is called the aerosol cloud interaction parameter. And a negative, you know, ACI is the Antitomy effect, while the positive one is the Tomy effect. And we're seeing over a lot with a, you know, a longer period, and also we're trying, you know, we've been very careful in taking out of this confounding satellite related problems. And this is work in progress. So we're seeing this over India, and this is, you know, unexplained. And so this is something also interesting. I think I want to leave some time for discussions. Let me quickly go over rainfall. I'll skip this. I think Dr. Krishnan has basically said a lot of this, and tell you what are the kinds of signals we're finding over the Indian region. And he had pointed out that if you look at the aerosol forcing and the response to the aerosol forcing, that is the drying, while the greenhouse gas effect is a wet getting wetter because of thermodynamics, right? And so here we're looking at the aerosol effect with these 40-year simulations, again, same model, general circulation model. And, you know, we're limiting it to not going out to 2100 and so on, but what is the climate change that's happening now? And so if we look at the difference between 2010 levels and 1971, which is what we did in this study, there's an intensification of drying is the model response, right? So that is detected, and it's linked to large scale circulation. So we did pairs of experiments where the sea surface temperature was allowed to evolve versus kept at a fixed level, and the aerosols were kept at different levels. And so we were able to pull out, you know, what the sea surface temperature largely acting through the Hadley circulation changes, and mesoscale convective activity, tropospheric stabilization, and various other things, which were the aerosol effects. This is a more recent work, Kaushik Muruturu. And what we're looking at is the fact that, you know, both stratiform and convective precipitation are not as well represented in terms of physics as we would like. What's interesting is that, you know, convective, with increases in aerosols, convection and convective precipitation is suppressed. I should also say that, you know, but stratiform precipitation has a very strong spatial heterogeneity, being increased in some region and decreased in other regions. And I should also say over here that, you know, many general circulation models have challenges getting the fractions of convective and stratiform precipitation right. This particular model seemed to do quite all right. But what we're basically showing is that this spatial heterogeneity came from, you know, the sort of energetics where we had these fast adjustments and changes in horizontal wind, a dynamical effect, and bringing in a lot of moisture. So it was sort of more of a synoptic scale moisture effect that drove why we had such an increase in stratiform precipitation. And, all of this is just saying, how does rainfall form? And so this is saying a Q, which is a liquid water, how it changes as a function of time. And of all of these processes, condensation, evaporation, deposition, etc., etc. But there is this one process called autoconversion, which is when does a cloud drop grow large enough to become a raindrop? And the way it's parameterized is with positively to total, cloud water, and negatively to the numbers of, aerosols present really. So it's trying to capture some of these effects, but we really don't have an explicit linking between what's happening to the aerosols and what's happening to the clouds, but also sort of, a lot still remaining to be done in terms of convective and stratiform precipitation. And this is the last thing. That extreme rainfall may have different signatures than mean rainfall, and however, if this comes from a lot of the studies have really looked at 1950 to 2000 or 1980 to 2005, right? And they are extracting this particular study, Deepti Singh et al. In Nature, extracted a wet getting wetter, dry getting drier, and didn't have any, link to aerosols. Others who have looked at with aerosols seem to indicate that the response to aerosol forcing is stronger than that to GHGs, and that different spatial domains, statistical thresholds, etc., might give you different results. And so once again, this is Prashant Dave's work, which came from observations. And we were able to show with correlation and causality analysis that there is a sort of intra-seasonal suppression of aerosol, which is the black of precipitation, black by the red aerosol. This was with a 5-day lag. And this was, extracted out of high aerosol, low rainfall regions, and from, once again, IMD rainfall and satellite detected aerosols. And so then after finding this out, we tried to explain mechanisms using what is called reanalysis data, which are like models run with a lot of data assimilation to make them very, very accurate, or very, very faithful to actual meteorology, and found that, when we had high aerosols, it led to a certain stabilization of the atmosphere and a certain moisture divergence. So having seen that in observations, this has just been submitted, where we did simulations, but with, I've not shown it here in the interest of time. No, I don't have it. Which is, in the last 20 years, there's been an unprecedented increase, something like a 15% per decade increase of aerosols in central India, which is also the core monsoon zone. So we used simulations during this period, which was 2005 to 2014, and with our emissions inventory, which is has the steep increases in recent aerosols, which is not there in the global models. And with that, we have some interesting results. I think I won't. So the causality and the correlation with, in this case, dry getting drier, but wet also getting drier, in terms of the fact that dry frequency went up, dry intensity went down, wet frequency went down and intensity also went down. And for many years, there was a causality from the aerosols. And we have the same thing with the model where we are running it with present day aerosols versus pre-industrial aerosols, and find this, what I was talking about with the dry spell, increase in frequency, decrease in millimeter per day of rainfall, and wet spells, decrease in frequency, decrease in. So this is a wet getting drier as well. I don't know if this is of interest, but basically it's the same Prashant Dave mechanism, which is borne out here, which is the stabilization and reduction of convective activity and reduced moisture convergence that he uncovered. But the interesting thing in this model is that the drying of wet extremes is because of cloud microphysical changes induced by sulfate aerosols. So I think I'll just leave this here, and we can go to questions, which is there's a lot of still to be done work, and whether we're going to do it with offline models, theoretical models feeding into large eddy simulations. But at the end of the day, we'd really like the theoretical science community to make a link with these very large scale Earth system models, because that's sort of where we would be able to make a contribution to really explaining climate change. Okay, thank you.
Questions?
Hi, Chandra. Thanks a lot for a very clear and great talk. Sorry for my naive question, but going to the Antitomy effect, you showed, I think, data, right, if I understand, which showed the Antitomy effect.
Correct.
And I was wondering, sorry, I'm way out of field. How is that data gathered? Do you fly into clouds or what?
Okay. These data are satellite data. So these are to do with a satellite detected, I shouldn't do this. I'm trying to escape out of this. So yeah, so these are data that in both cases are from satellite. I don't know, is this visible now, the screen?
Yes, it's visible.
Okay, it is a satellite detected product of what is called cloud drop effective radius. In this particular case, and so those are the data that are available in space and time. We're looking at region 2, which is, sort of this monsoon region over here. And in this particular study, what we did was we separated out what we called the deficient monsoon years, but the abundant and the abundant monsoon years, and really found this kind of an antitomy effect with the abundant monsoon years. There's plenty of caveats, which is that satellites detect aerosols, and they do it with a footprint of maybe right now it is at a few hundred meters, but in a pixel where there is a cloud, you would not detect aerosol because the cloud optical thickness is very high. And so then what we are using is sort of a consolidated product which is released by the satellite sensor community, which is not accounted, which is at 100 kilometer, which is basically saying this is sort of a mean average over what's happening over there. So indeed, at the location where you are able to detect cloud drop effective radius, you would not detect aerosol, right? So it won't be exactly co-located in space and time. There are, of course, aircraft campaigns. Indian Institute of Tropical Meteorology has done some of them. I understand there's been sort of paper, at least a conference paper from our colleagues there, which is showing something like this with what's called in situ measurements within the cloud. This is still not accepted very well by the satellite community. And so we've tried to do a lot of parsing. The criticisms are, if you are looking at a broken scene of clouds, if you may have aerosol being erroneously detected where it's really a very thin cloud. So you need to not look at low water availability. You need to only look at the very highest water vapor availability or precipitable water. So we've tried to do all of that in this ongoing work, and we still see the effect, which is you're increasing the number of particles, but the moisture is not distributing to all of them. Somehow only a few of them grow much larger, and so we don't know what's going on.
I see. Okay, thank you very much.
Aditya?
Hello.
Yes.
Regarding the anti-Tumi effect, is there a fundamental understanding of why it occurs?
Okay. I think the best so-called the best investigation is sort of based on large eddy simulations, and there's two possibilities. One is that it depends upon the aerosol hydroscopicity. If you have aerosols which are considered to be, it's called very slightly soluble, because particularly in the Indian region, we have a lot of biomass burning, and we have aerosols that may not be that hygroscopic and can nucleate clouds. If you have a large number of those kind of particles, then the number of particles is high, but the numbers on which you can have the condensation is still pretty low. So there is either slightly soluble organics, or a very few giant cloud condensation nuclei, which is what the IITM colleagues said, that these come during the monsoon. You have these huge 1-2 micron sized salt particles coming in from the ocean. So in such cases, you will activate only a few particles, not all of them, and then the moisture preferentially goes there. That's speculation, but it hasn't really been looked at. You can see this is 2008, and there really isn't anything in the literature definitive about it yet.
Since you mentioned biomass burning, can you comment on the, terrible pollution in Delhi and other parts of North India, and whether you think that will have some effect on climate change and what causes it?
The first part of the question is that as far as air pollution goes, and our understanding is that the scale is not city. The scale is 100% regional. And that is the scale on which we need to understand it, and we need to control it. So that is one. The other thing that we understand from sensitivity simulations, turning on and off sources, is that a large part of the pollution comes from what we call non-formal sources, which are your biomass, which is your chula use. Everybody's cooking every day, and we have failed to provide clean and affordable energy in our country to our fellow citizens. So there is only biomass available. And so we have chulas, we have seasonal agricultural residue burning. We have a lot of open waste burning. And we also have lighting with all sorts of, now there is a big push to, clean cooking and clean lighting. But again, there are various challenges. So there's this large regional background of pollution, which is not coming from only industry, transport, thermal power. And that's where the focus of the control has been. So, I mean, that's the pollution story. And is the pollution affecting climate? That's what we showed in terms of heat waves, in terms of mean rainfall, extreme rainfall, and clouds. So indeed, the pollution is affecting climate, both mean and extremes.
So this phenomena of aerosols affecting monsoons, has that been observed across the world or only in India?
No, it's observed across the world. And what Dr. Krishnan was pointing out is that you have this interhemispheric asymmetry in the energy balance, that the northern hemisphere has a lot of aerosols, and therefore you would have a difference in the ground reaching radiation, while the southern hemisphere is brighter, and so that's weakening various dynamical changes. So this is what has been looked at as a weakening of various monsoon systems. What has been shown on a regional scale is the East Asian, I'm more familiar with the East Asian and South Asian monsoons. I think Dr. Krishnan also alluded to the African monsoon. I'm not that familiar with the literature, but East Asian, South Asian, there's, other than the global phenomenon, there's a lot of nested regional phenomena, including fast responses. And it's borne out in the measurement data. We've had a reduction in mean in mean rainfall over several decades, and this continues over India in the recent decades as well.
I see. So if one were to think of aerosols, harmless aerosols as a solution to lowering temperature, that would be a bad idea. I mean, this would be one consequence, that the rains worldwide would suffer.
Yeah, we don't know. It's very, very let us say it's a very, very non-linear and dynamic response. So we don't know where it's going to shut down, when it's going to shut down, and how much it's going to shut down.
Any question in the chat, online viewers? Yeah, there's one question here.
Okay, yeah, let me see. Can you give some insight into improvements needed in turbulent heat transfer? So, I'm not the expert. So all I can say is it's natural convection mediated, and we kind of need to look at when you have a surface that's much hotter and a surface that's probably of different roughnesses, what that might do, and what that that's sort of where I would stop trying to say anything more, Vishnu. You'll have to ask people who are better experts on that.
With your talk, Chandra, you've given us a lot to think about. We'll be back asking you more questions. So thank you very much for this nice lecture.
Thank you very much for all the interesting questions. It's been a great pleasure. Thank you.